All right, everybody. Welcome to Dunsink Observatory. My name is Peter Gallagher. I'm the director of the observatory. We get the pleasure of working in this building every day. There's about 15 of us working here, PhD students, research fellows, professors, and there's another maybe 20 of us in the city centre as well, all working on a variety of things from the sun to galaxies to stars to all kinds of bits and pieces. But this evening, we're here to hear about a brilliant new mission called the James Webb Space Telescope. And no better man to tell us about it than Paddy Kavanagh. Paddy is a research fellow in the school, and his job is, well, twofold. Number one is analysing data coming from the James Webb Space Telescope. So he sees the cool images before any of us. Lucky man, but also he had the pains and trials and tribulations of being there before launch and getting some of the software ready for the telescope, and then at launch watching €8 billion or US dollars of hardware going up into space and 30 years of thousands of scientists' activities. So welcome to Paddy, and Paddy will speak for about 40-45 minutes, and afterwards we'll have some questions to ask them really hard ones. So kids in the room, start thinking of hard questions. The first question is to you guys, okay? First question and last question is, okay? Thanks, Paddy.
Thanks, Peter. Wait till the end. So thanks. It's very, very nice. It's the first time I've spoken at Sound Augur Science. Even I've been working in DIES for 6 or 7 years now, and it's a really great year for me to do it. I think because, as Peter mentioned, it has been an insane, crazy, scary, you name it, year. But I'm very happy to be here tonight to talk about Samhain, because obviously, as you can tell, I'm Irish. So like Samhain and Halloween mean a lot to me as an Irish person, and all of you, I'm sure. But I mean, a lot of people don't realize is that Samhain and Halloween, it has astronomical background. I mean, it's the date is set because of astronomy. Okay, so Samhain is actually one of the 4 cross-quarter days in a year. So all that means is that between the winter solstice and the autumnal equinox, so the point at which halfway between the equinoxes and solstices are called the cross-quarter points. Okay, and Samhain falls here on the 4th cross-quarter point in this diagram. And it, as you probably know, it marks the end of the harvest season and the start of the winter. Okay, so it was always a festival to celebrate sort of the end of, the summer and the start of the long, cold winters and so on. And I mean, it's built into our heritage here in Ireland, Samhain, because even these, you're all familiar with what passage tunes are, and everybody's familiar with Newgrange and how in the winter solstice the sun would shine in through the passage and light up the chamber. But Samhain is just as important back then. So there are plenty of passage tunes around Ireland where the sun will shine into the chamber on Samhain. Okay, so 2 examples. One is up in, this is at the top of Tower Hill. Anyone who's been to Tower Hill would have seen this top passage tune, which is called the Mound of the Hostages. For some reason, I've no idea why. And this one here is in Carrowkeel. So Cairn in Carrowkeel is also lit up on Samhain by the rising sun. And even at Newgrange, in the Brina Buena complex, there are kind of alignments of buildings in that complex that point to where the sun rises on Samhain. So it's incredibly important for pagan Ireland and the builders of these structures. But even more astronomically related is that Samhain is often associated with the Pleiades star cluster, because it's at this time of year that the Pleiades, I'm sure everybody knows what the Pleiades are, do they? The open star cluster, of course. But this rises at dusk around this time of year and sets at sunrise, and it reaches the highest point. It reaches in the sky at midnight. Or historically, it doesn't anymore because of precession. But back when these things were built, when these passage tunes were built, and the date for sound was being set, this would have happened on the 31st of October. Okay, or what we would call the 31st of October. And the Pleiades also are associated with the afterlife in lots and lots of cultures, with the otherworld and the afterlife and all of this, including here in Ireland. And that's why at Samhain, as you're all aware, it's said that the gates to the otherworld open and the dead can walk among the living. Okay, and that's where we get Halloween from, and the guys, like, you know, dressing up and all of this kind of thing. So that's sort of the origin of where these kind of pictures come from, where on, you know, this one day a year, and it also happens in Bealtaine actually. So the next one, it's also the door to the otherworld open, but for some reason Halloween's stuck. And you get pictures like this, you know, where the door is open and all of these creatures and mythological ghosts and ghouls and whatnot come into the world and can interact with the living. And it's really not as bad as they make it out here, because often it would people who would want to talk from the other world, not demons and ghosts and so on. But yeah, I mean, so it was an incredibly important astronomical event, and it had all of this kind of connotations with the afterlife and everything. So, I mean, even today, you know, looking into space with the most sophisticated instruments people have ever built, you still see some aspects of these afterlife type things, like these, you know, ferocious hellscapes where there's demon horses and kind of something burning in a pit of fire over here, or this unbelievable image of the ghost and women and children screaming as you see this ghost moving away, you know, or witches. Plenty of witches in the universe, and ghosts, real ghosts, Ghostbusters type ghosts, or, you know, really dark and shadowy eyes looking back at you through your telescope, or ethereal hands about to strangle some unsuspected nebula. Okay, so and some god awful one-eyed black two-armed floating thingy that must have come from some afterlife. But I mean, all of this stuff is sort of when you look out into the universe with modern telescopes and modern instruments, you see all this unbelievable, breathtaking kind of, you know, variation in what's out there. And, you know, if you're seeing all of these sort of scary things when you look out into the darkness, then you have to ask yourself, why? Or do we keep looking into the darkness? Why do we keep finding this type of stuff? Well, the answer is simple. The answer is because the darkness holds the secrets of the universe, okay? Inside of all these things, there is physics, science going on that defines and dictated how the universe evolved and how we got here. Okay, so you want to look into the darkness. Two regions of darkness that are very, very important for us are star-forming regions, molecular clouds and star-forming regions, okay? So this is like the raw material out of which stars and planets are built. But it's, when you look at it, something like the Hubble Space Telescope, you're looking at it in optical light, so light we can see with our eyes. But what's happening inside of these molecular clouds, where stars and solar systems and planets are forming, which we want to understand because that's where we came from. You can't see into them because the light is blocked by the clouds of gas and dust, okay? That's one reason you want to look into the darkness. And this is just some, you know, zoomed in kind of small globules. And inside of these clouds, there's stars and planets and solar systems forming, okay? And you really want to look in to try to understand how all of this happens. What about the universe itself? Everybody probably has seen this picture before. This is the Hubble Ultra Deep Field, where once, a good few years ago now, Hubble stared at a particularly uninteresting part of the sky. Okay, so it picked a kind of an empty part of the sky and said, we're just going to point the telescope here. And, you know, the way Hubble works is it will come back around and keep pointing at it and keep pointing at it. And it did so for, I think, the best part of a month, staring at the same patch of sky, which was thought to be empty. And it took this image, and every single point in this image is a galaxy. Okay, so every single point is billions of stars looking back through the universe. Because light travels with a finite speed, okay, it takes time for the light, for some galaxies in the distant universe to get here. It takes billions and billions of years. For closer galaxies, it takes less. Okay, just So, you know, the sun, like light from the sun takes 8 minutes to get here. So as you move further and further away, it takes longer and longer for the light that was emitted by these objects to get to us. So when we see an image like this, we're seeing some stuff that's nearby that, you know, we're seeing as it was a couple of 100 million years ago, but you're also seeing the more distant things. Distant, like these small red galaxies, they are billions and billions of light years away. Okay, it takes billions of years for the light to travel from those objects to reach our telescopes where we can see them. Okay, but Hubble can see all the way back to the first stars and galaxies. It can see back reasonably far, but it can see all the way back into the darkness behind these galaxies where the first stars and galaxies formed. And we want to know how the first stars and galaxies formed, what did they look like, when did they form, how soon after the Big Bang, okay? You just can't answer with something like Hubble because it was designed to see optical light and some other types of light, but the light from the most distant galaxies, you can't see with Hubble because it's not designed to detect that. Okay, so what you need to do to look into the distant universe or to look into the cradles where stars and planets are being formed is you need to design a special type of telescope, one that sees in a different light to Hubble. Okay, where that light can pass through dense knots or through can see the most distant stars and galaxies in the universe. Okay, and that's where this telescope came from. That's where the James Webb Space Telescope design and concept and it was where it was born. Okay, it was designed to answer the big questions Hubble couldn't, simply because Hubble was never designed to do it. Okay, even though it's an absolutely amazing telescope. This thing was designed to see the first stars and galaxies in the universe, and it was designed to see into where stars and planets are forming. So we can understand how the universe got started and how we evolved and how, you know, galaxies evolved in it and how stars and planets are now forming, which will tell us how our solar system formed. Okay, so I'll come back to the design, but what JWST sees, okay, so the James Webb Space Telescope, what it sees is infrared light. Okay, and you're all familiar with infrared light from something like a thermal camera. Okay, or I was giving a talk myself and Peter, actually, I think you were there as well when we were talking to the group in Kansas. Remember? And we were trying to explain the idea of a thermal camera, but it's like a thermal sight on a gun. And it was a concept they all got. But anyway, so this is a scientist at maps, and he's just holding a black plastic bag over his arm. So we can't see what's behind that bag just because the optical light is absorbed by the bag. So we just can't see what's behind it. But if we look at the infrared radiation from him, okay, so we're seeing the light that's being emitted from him. So it's his heat that we're seeing, okay? That radiation can travel through that bag and we can see what's underneath it. And that's what James with the JWST looks at. It looks at that heat radiation coming from the universe, okay? And that's important because that radiation can travel through this kind of material, so it allows us to see into where the stars and planets are forming. When you're looking into the distant universe, right at the very start, you're seeing light that was actually emitted as optical light. Okay, so Hubble should be able to see it. But because that has had to travel for so long through the universe, and the universe has been expanding ever since the Big Bang, right? So that light is traveling through expanding space until it reaches us. And the effect of that is that optical light, or sometimes UV light, or even more energetic light, gets stretched. Okay, so what was once optical or UV light has become infrared light to our eyes. Okay, but for us, we need an infrared telescope to see that light in the very first stars and galaxies. Okay, and this is a small schematic just showing you the difference between Hubble and JWST. That Hubble can see so far, but it's just physically not possible to see any further than that with Hubble because the light has been moved, the light has been stretched out of Hubble's kind of eyes. Okay, just can't see it. But the JWST was designed to see all the way back. Okay, so the light that was emitted by the very first stars and galaxies is being stretched, but not out of the sight of JWST. Okay, and there are two things that drove the design of the telescope. So you'll see here, it's quite an unusual looking thing. All right, it's not like your classic picture of a telescope that's in a tube, no big mirror in a tube. The mirror is exposed. It sits on top of this, layers of tinfoil, basically. Now, the reason it looks like this, there's two reasons it looks like this. The first is that it's a big mirror. Okay, it's 6.5 meters across. So I don't know what 6.5 meters is. It's good, not far off the size of this room, width of this room. So it's a pretty big mirror. You want to put that thing in a tube, you're never going to launch that into space. Okay, there's no rocket on the planet that could put that thing into space. So the only way you can get a mirror this big into space is by creating a segmented mirror that folds up. Okay, so you don't need a tube, it has to be exposed. And what about this thing? Well, as I said, this is designed to detect heat radiation, okay, which means you have to keep it all very, very cold. If you don't keep it cold, all you're going to see with your telescope, with the instruments that are in here behind the mirror, is the mirror itself. Because the mirror will be warm enough that it will emit the type of radiation you're looking at. Okay, so it would be like trying to see a candle in a furnace, right? You just never be able to see it. So to see the light you want in the distant universe or in star forming region, wherever, keep everything cold, and that's the function of this thing here. We call it the sun shield. Okay, so it's 5 layers of very advanced tinfoil, really. And it reduces the temperature. So this side down here almost points towards the sun, okay, and the earth. So the sun and the earth are always on this side of the telescope. It reduces the temperature from nearly 100 degrees on this side. Okay, so this side is very, very warm, to minus 240 on the top side. Okay, so everything here is about minus 240 or less, minus 250 or less. Sorry, minus 230 or less. So it's kept very, very cold, and that's why it looks the way it does. Okay, so I talked about the sun shield in the mirror. By the way, you need the big mirror as well. We didn't mention the big mirror, the big nice gold mirror, which is gold because it reflects infrared radiation. It reflects the radiation very well. But you need a big mirror because if you're looking at the first light in the universe, the first starlight in the universe, you need to collect a lot of it. Okay, because it's very, very faint. So if you don't have a big mirror, you're never going to get enough of it to see in your image. But that mirror comes with an added bonus, is that when in astronomy and in optical theory, if you have a big mirror, it means you can resolve more detail in your images. So your images will look way sharper with a big mirror than a small mirror. Okay, that's why if any of you are amateur astronomers, if you go to buy a telescope, you can buy a small one cheap enough, a couple €100 or something for a pretty decent one. Once you start to grow in size, to really look at detail on the planets or anything, you need to get those bigger, more expensive ones that cost thousands of euros. So the reason is that with the bigger mirror, the bigger lens, you get more detail in your image. Okay. So how do we've been involved here in DIAS with James Webb now for about 15 years. And DIAS's contribution is actually one of the instruments that's on the telescope. Okay, so NASA built the sun shield and mirrors and these things. Europe provided 2 of the 4 instruments, MIRI and NIRSPEC, were part of MIRI and all of NIRSPEC. Then the Americans provided NIRCam, and the Canadians provided NIRIS. So the whole thing is a collaboration between Europe, America, and Canada. But we provided components for the mid-infrared instrument, so it's the instrument that sees heat radiation from stuff that's a bit cooler, okay, than the near-infrared. Near-infrared just means it's a bit hotter, but still it's heat radiation. Yeah, so we've been working with it for about 15 years now, providing some of the components of the instrument itself, then working on developing the software and calibration tools that are necessary to turn the raw data. So I'm sure you've all seen some images from this. They all don't look like that when they come down from the telescope. Okay, they go through a series of a whole process and pipeline to remove unwanted artifacts and imperfections in the image, and that's what we do, right? We work to understand all of those imperfections and all of those artifacts and remove them to leave the clean, science-ready images that you see in the press and see that have been released to the public. Yeah, and you know, we were all talk about, you know, ghosts and witches and all of this kind of thing, but I was never more terrified than I was last Christmas Day. It was the worst Christmas Day I've ever had because, as Peter said, 10 billion euros worth or $10 billion worth of the Space Telescope is sitting in the nose cone of this Ariane 5 rocket in French Guiana. And at about lunchtime, our time, it launched and went off up through the clouds. And everything went extremely well. After all the nervousness and, you know, all of the work and so much goes into something like this, I can't even explain to you. So it goes up under the clouds, but then we can switch to the simulation so we can see what's going on. So the launcher was provided by Europe, by Ariane Space. What happens is that, you know, it gets up so far, it gets delivered into its path out to where it's going. And they did such a good job of this part of it, of launching this telescope, okay, that the only consumable on the telescope is fuel. So it needs a little bit of fuel to kind of keep itself where it is in space, okay? When it was launched, they put it on such a perfect path to where it was going. It didn't need to burn as much fuel on the way. And because that was our only consumable, that means that it extended the lifetime of the telescope. Okay, and it didn't just extend it, it doubled the lifetime of the telescope. It was originally planned to last for 10 years. But because of the job that was done on Christmas Day, when everybody was, you know, so nervous, the people at Ariane Space, I don't know if anyone watched it or saw the video, they were checking their phones, looking at Twitter, and so they didn't even care. They do it every month. You know, the rest of us were like, you know, shivering with fear. But they launched it, they put it into the perfect orbit. And this video was taken by a camera in the upper stage of that rocket. And this video, that took the video, developed by a company here in Dublin. This video, or this camera, was built here in Dublin by Rail for Space Systems Engineering. And this shows the last real look we got at the telescope as it left the upper stage and headed on to where it was going. Okay, so it was such a successful launch and a successful day. So as you can see here, the telescope is folded up, right? You have to fold it up to get it into the rocket. What follows is a series of deployment steps where the wings come down, the structures come down that hold the sun shield spreads out, deploys, and the mirror unfolds out. Okay, so there's lots of different steps, but overall there was 384 single point failures in this deployment. Okay, so that means that if any one of those 384 deployment steps goes wrong, it's a $10 billion piece of crap flying through space. Okay, and it took 2 weeks, and it was I'm glad I wasn't there. I wasn't in America at the time, but I mean, it was the most nerve-wracking 2 weeks for astronomers all over the world because we knew this was happening, and everybody's been waiting. Okay, it's been developing for 20 some years. Just one of those things goes wrong in the space jump. Okay, but in the end, everything went absolutely perfectly, and and the telescope was successfully deployed in January. And that's when fun started. That's when Peter's talk of, you know, months of hell and stuff came into being, because all of the scientists who work on different parts of the telescopes flew over to the US to work on our own specific part to check that everything worked okay and ensure that the telescope and the instruments were ready for science. Okay. And yeah, I was there for a few months in the summer this is the MIRI team. So this is our European team, European and American team who commissioned MIRI back in June now. So this was on the 29th of June. Oh, sorry, no, it was near time last. Yeah, so it was the 10th of July. Okay, on the 10th of July, one of the other instruments went through the last check of commissioning to make sure everything was okay. And all of the different instruments and modes on the telescope had been finished. Okay, everything was ready to go. And now we could start to release the telescope for science. And the first thing it did was take the images that were released to the public. And the first one of those was released by President Joe Biden, okay, in a ceremony on the 13th or 14th of July, or 12th, I can't remember. But it was the Sunday night before the official release, and there was a small ceremony in the White House where they showed the very first image released to the public from JWST. And I come back to it in a second. We also had lots of our own stuff here in Dublin, including this really nice evening where our Professor Tom Ray, who led the Irish involvement in MIRI and JWST, showed the first images at the National Concert Hall. Okay, at an event to mark Apollo. But yeah, it was a really crazy time because we just come off the back of all of that work, and then suddenly these images were out, and the kind of press insanity that followed it was unbelievable. But going back to that image released by President Biden, I showed you the Hubble Deep Field. Well, this is MIRI's first deep, or this is JWST's first deep field. Okay, so it's the same idea. It picks a part of the sky and stares at it, and it sees further back than that Hubble image. Okay, and I told you that the Hubble image was looking at the same part of the sky for the best part of a month. This was done overnight. Okay, so this is the leap forward in capability and science that was possible with this telescope. And when you're looking at this, what you're actually looking at, as I said to you before, you're looking through cosmic time, because the stuff that's closest to you looks how it did a couple of million years ago, whereas the stuff really far away looks as it did billions of years ago. And in the center, there's a galaxy cluster, okay, and it acts as a magnifying glass in space. Okay, it just deforms space. I won't get into the physics of it. This is kind of a schematic of what's happening. But the galaxy cluster in the middle, which is all of those white galaxies, deforms space, and the light from the stuff behind it gets bent around the deformity before it reaches us. Okay. And that's, if you zoom into the center of that image, that's what you're seeing here. Here's a galaxy cluster. Here you can see all of this distorted stuff. Right, this isn't imperfections in the mirror or anything. This is the light from the galaxies behind the cluster being, deformed by the curvature of space. And actually, this galaxy, and all of these are all the same galaxy. Okay, they're just coming out around the lens and coming back into our lens slightly differently. So this is an amazing image. You can see all of this weird stuff, like these small distant galaxies. The stars are the looking things. But even this galaxy here has all these dots around it. Those dots are massive star clusters in those galaxies. It's the first time anything like that has ever been seen. The amount of science in that image, in that one image, here's another part where you see again the deformity of all of the galaxies. These distant small red ones, there's a few here. They're some of the first galaxies in the universe. Okay, nothing like this has ever been seen. And weird, really weird looking things like this. I don't know what that is. It's called a chalice for some reason. It kind of looks like a chalice. But yeah, you could scroll around that image for hours and find something interesting in every part of it. But yeah, that was the first image, and then we go on to stranger stuff. The telescope also looked at galaxies that were still forming through interactions. Okay, and this is a picture with our instrument, MIRI. Of a grouping of galaxies called Stephan's Quintet. So there's 5 galaxies, there's 2 here, there's one down here that's to the left of this one. But these are all physically interacting with each other. Okay? These are all moving through each other, and what you're seeing is them stirring up all of remember I showed you the picture of the molecular clouds and stuff, which where stars form. But what's shown here is the gravitational and tidal interaction of these galaxies is stirring up all of that kind of material in the galaxies and spreading it out all over the place. And it looks like fireworks almost. Okay, and that's where star formation happens, because when you disturb galaxies or when you disturb gas and dust like that, you form stars. And you can see out along here, these are all star forming regions where these 3 galaxies have had a massive interaction. So this was one of the first images that was released as well. Okay, and there's been other images since, like this crazy image of what is basically the skeleton of a galaxy. So we're used to seeing something like this with Hubble, where you can see all of the stars and dust that's blocking the light from the back and so on. But when you look with JWST, you're seeing that gas and dust where the stars are forming, and it's basically the bones of the galaxy. Okay, that's where stuff is forming. And you can see all of these holes sprinkled throughout. Well, that's where the massive stars are blowing massive bubbles into the galaxy, into the interstellar field. some massive stars and supernovae are carving up the interstellar medium, and again, that drives star formation. You can see all these bright around where all of these stars are forming. So this is really showing us how star formation evolved in the universe through all of these galactic tidal interactions and, you know, massive stellar feedback. The first image of this galaxy, which it came to be known as the Phantom Galaxy. The first one they released of it was this, which is a scary looking thing, right? But I think they missed a trick. Does anyone watch Stranger Things? We should have called it Vecna's Galaxy. This is exactly something like the background of that. You know, yeah. Anyway, I mean, this was my favorite image of the telescope for a long time. This is a picture of a star forming region here in the galaxy called Carina. What you're seeing here is you're seeing all of it's along here. You can see all of these stars and these kind of outflow type things. They are all young suns that are forming. Okay, we came from something like this. Okay, and all of the stars form these dense lumps. And what's happening is all this blue stuff. There's massive stars up here, massive stars emit a lot of energetic radiation, and it's kind of evaporating off all of this dense material in the blue coming up here. You can kind of see it. But what it's also doing is putting pressure on that cloud. If you put pressure on clouds like these, it causes stuff to contract, and that's when you get stars forming. So you can see inside all of these dense blobs. We're seeing through them now because we can see through them with the infrared radiation. But with, you know, this is with near infrared, which is, you can see through quite a bit, but not altogether. But then this is with MIRI. So you can really start to see through all of these now. And all of these red stars, these are like stars in the very earliest stages of star formation. And we can tell so much from looking at this. And you can see them all over here. We've never been able to see stars and solar systems at this stage before. Okay. So that, you know, the science that possible is unbelievable. So what about our future? I mean, we want to understand where we came from in the universe, but we also want to understand where we're going. For those who don't know, the sun will you know, pack it in at some point in about 5 billion years. But what will happen is it will start to shed its outer layers. It will grow very, very big, and it will start to blow off its outer layers. And this is what it will look like. Okay, so this is a picture of the future of the solar system. And our solar system at its current size will fit comfortably into the center here. Okay, so at some point in about 5 billion years from now, the sun will you know, start to give up, shed its outer layers like this, and all of that would plow through the solar system. Okay, now what's around by then, I don't know. Whether people will still be around by then, I don't know. But the detail provided by the telescope really allows us to look at this stage of these last stages of the evolution of a star like the sun in unprecedented detail. One thing I haven't mentioned so far is exoplanets. The telescope is designed to study planets around other stars. And a couple of months ago, we had the very first images of an exoplanet with JWST. Now, this isn't the first in general. Like, there have been images of other planets around other stars before, but this is the first time JWST did it. But it's being optimized to look for specific things in the atmospheres of exoplanets. So just in terms of direct imaging, it looks at specific parts of the electromagnetic spectrum. And basically what you can tell, if you look at a planet orbiting a star over the course of a year or 5 years or whatever, you could see changes in the brightness of that planet that could be related to stuff like vegetation or ice cover or clouds, you know, all of this kind of stuff. So we can start to understand the planets at that level. But even more incredible is that we can actually figure out what's in the atmospheres of those planets. Because if we look at planets that we know are crossing the host star, okay, and we do know quite a few, when that planet crosses the star, some of the star's light will be absorbed by the atmosphere. Okay, so here there's a small atmosphere, there's no absorption of the light, so the spectrum looks like this. Okay, so this is just telling you what's in what light is coming from the star. So if that atmosphere is there, this can absorb some sun's light, and you can see that where these dips happen will be at very specific. We'll tell you what's in there. It'll be caused by very specific material, which we understand from physics spectroscopy. And the telescope is designed to do that, okay? And it's already done it for a few planets. This is the first one that was released, and These aren't Earth-like planets, these ones. Okay, just so you know. This is a hot Saturn, actually. A hot Saturn. It's a Saturn-sized planet that's very, very close to a close star. But what you see in the spectrum is all of these peaks here, and that's water. Okay, so there's like steam in the atmosphere of that planet. It's so close to a close star that you're just seeing steam in the atmosphere. There's also this planet here, which is what it's called WASP-39b, but this one they detected carbon dioxide. This is the first time carbon dioxide had ever been detected on an exoplanet. Okay, this is a big Neptune. Okay, again, we would be looking at anything, any constitutes of life or anything here. But the plan is in the future that it will look at super Earths. Okay, we'll try to see what's in the atmosphere of super Earths, and it will look for stuff like, you know, is there anything that could indicate the presence of life, presence of industrial civilization? Now I'm being it's very unlikely that they'll find something, right? They'll have to be extremely lucky, but the possibility is there, and it could detect that if they hit that 1 in a billion jackpot. Okay, it's also started to look into our solar system. So we saw this beautiful image of Jupiter. And all you're seeing with Jupiter is this kind of reflected sunlight, okay? So that's why, well, you're seeing the aurora, like, much like on Earth. The rest of it is just reflected sunlight. That's why this spot looks so bright. It's actually higher up the atmosphere, the clouds are. So it just is reflecting a little bit more. And you're seeing some small moons in Jupiter's ring. My new favorite image since the Carina image is this picture of Neptune. Okay, because I think this image probably holds the record for having the nearest thing and like the greatest contrast and distance probably of any image ever taken, because we have something in our solar system, Neptune, and this is Triton. By the way, this is Neptune's moon. But in the background, you have all of these galaxies that are billions of light years away. Okay, so the telescope is designed to be a high contrast instrument. You can see stuff that's nearby and very bright. At the same time, it's looking at something that's very distant and faint. And you can see it in this image. You see all these galaxies pepper in the background, and a bright kind of pearly jewel in the middle there is Neptune. For those who follow astronomy a bit, you may have heard of the DART mission a few weeks ago. It was a kind of a Armageddon type experiment where if there was a comet coming towards the Earth, you could fly a satellite into it to knock it off course. And NASA tested this a few weeks ago by crashing a satellite into this. I can't remember if it's a comet or an asteroid, but you have to look at it very quickly now. So this is what it would normally look like. But Webb was looking when this happened, when this interaction happened. You can see there's just that explosion of material off. So it's really kind of, you're looking at the asteroid as that, the satellite, it's called DART, I can't remember what it stands for, the double asteroid, something test, double asteroid redirection test. So it has, you know, the telescope is amazing. It doesn't, you know, it was designed to answer specific questions, but it's general purpose observatory. And they can look at anything in the universe and make groundbreaking discoveries. The last image I'm going to show is just this one, because this is the one that was released last week for Halloween. Okay. And this is an image of what are called the pillars of creation. Okay, so this is a very famous image taken with Hubble, where it showed these great gas pillars sticking out like fingers into a star-forming region. But as I said to you before, Hubble could never see through the gas and dust to see what was inside, to see what stars were forming or what solar systems were forming. But JWST absolutely can. And this was taken with our mid-infrared instrument. Okay, so it's a really, really nice image. And like, it was made for Halloween. That's why it looks orange. It's people just assign colors to make, you know, to make it Halloween. But you can see through all of that gas and dust. And what I find amazing about this image, it's supposed to look scary and Halloweeny, and like, you know, my wife keeps saying it looks like Dementors in Harry Potter, you know, flying. But actually, it's the exact opposite of that. It's a stellar nursery. Okay, it's not showing you stellar death or dead or scary stuff. It's where stars and solar systems and planets are forming. And at the end of all of these small, dense protrusions out of the cloud, you can see there's a red source. See that? Here, 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 here. They are all incredibly young solar systems that are forming. Okay, so you're looking at the babiest of baby stars and planets and solar systems in this one image that was released for Halloween. As scary as it looks. But I leave it there. But I often, when I do these public talks, I always leave everybody with one thought. Okay, is that all of the images that I've shown you were picked because the scientists didn't want to observe, because they weren't interested. Okay, so if this what's been released to the public in 3 or 4 months of observations, and the scientists are working on what they really wanted to look at and the biggest discoveries, just imagine what's coming. Okay, and I'll leave it there. That's 45 minutes.
Having put an amazing achievement to build this telescope for 30 years, it's 20 meters long, it's 6,000 kilograms or something. You know, it's the size of half the size of a Boeing 747. It's enormous, and we've got them at the right place. And it's putting data that looks like that. Think about how hard it is to take a pair of binoculars and put them at a bird that's flying, you know, shaking all over this. This is an amazing achievement. And I'm so lucky to have somebody like Paddy and others who are working on this here in Ireland. So, anybody got any questions? And actually, yeah, the rule was kid first. So we had to have one kid ask the first question and one kid ask the last question. And we're not leaving the room. All right, come on, Kitty, get your brains thinking. Your only chance to ask a really difficult. Right past that.
No, don't try to touch that.
I'll flag them off and coffee tomorrow. It's going to be fantastic. Come on, please. Yeah, come on, flag them about.
Times on how long it would take to create a solar system?
Ooh, yes, it's a good question. It depends on the size of the star, but it can take, no, it depends on the speed. You're talking about 1 million years. It's probably less than 1 million years, but by the time the star forms and blows away all of the material around it to leave just the planets, it's probably 1 million years. 1 to 3 million.
That's a really good question. I teach 4th year in university in Trinity, and I spend 12 lectures teaching how to form planets and stars. So you have to do 1st year physics and maths, 2nd year physics, 3rd year astrophysics, and then 4th year we'll get to that question. Pardon?
20 class maker. I don't think you can pass all through this.
It is a bit like Danny Crosby. So, all right. So, any other questions then to the adults in the room? Yeah, down the back there.
There's 18 mirrors on the James Webb. One of them gets damaged. Can we still get an image?
Absolutely, yeah. I mean, you probably saw. So each one of the mirrors is can be controlled to a very fine precision. Okay, I'll just go back to it. Yeah, there's 18 mirror segments, and behind each one is a series of actuators. So each one can act as a single telescope. Okay, and like the first, when I showed you the picture of when the instrument or the telescope was deployed, it took about, those mirrors weren't aligned, and it took 3 or 4 months to get them all perfectly aligned to maximize the capability of the mirror. Each one is a series of actuators, acts as an independent telescope, and what you do is you focus each one separately and then bring them all together. And that's the idea. You've probably heard in the news that there have been impacts of micrometeorites on the mirrors, and that was expected because it's exposed. It's exposed to space. What can you do? It's been hit a few times. There was one that was a little bit bigger than was expected. It was still, tiny. It was less than the width of a human hair or something. But it did damage one of the mirrors to the point where that it couldn't be corrected by using the actuators, and it was like less than a % level effect. Now, of course, if a boulder-sized thing hits one of them, it's done. But the rest of them will still be fine. It will just change the PSF. It will change point spread function. So like this kind of hexagonal spikes you get coming out of it won't quite look like that. It'll be a little bit different. Yeah, but it can function fine.
It's an interesting project that you could do, you know, if you've got all of them, get somebody to knock out one and then see what the image looks like, then knock out two and then see what the image looks like, then knock out three and see what the image looks like. Just keep on doing it, but as an experiment on a computer, you can do it. Right, there was another, your hand was up down there, yes.
Yeah, are you able to see what the stars and solar systems? Like you can see now, like on the past stage around the cycle. Can you see if any of those solar systems are still in existence?
It's still in existence, you mean,
Like,
because
does it like taking so long to travel?
no, I mean that's our fundamental limitation is that it doesn't matter what we look at it with, light always travels at the same speed. So we can't see. No.
The analogy I like to use is when you're looking out into a forest, you see saplings and you see fully grown trees. And as humans, we can put a camera there and watch the sapling become a tree. You could wait long enough, but in space, you just can't wait long enough. So when you look out into space, you see some things that are just being formed, some things that are fully formed, and you got to kind of put them together.
Exactly.
By looking at them. You can't just look at things evolving. Now there can be explosions, like we had this gamma ray burst about a month ago. This is gamma, like this formation of a black hole was so big that it could wipe out all life in the galaxy that it's in. You know, it's an incredible explosion. So sometimes you get these bandits, but most of the time you're looking at a forest and nothing's going on. You just got to put the story together. Right. Oh, we've got two children asking questions. Yes, you can go through.
Can I see back to 200 million?
Yeah, it's after the Big Bang. So the JWST was designed to see the first starlight. Okay, so the first stars in galaxies, but there was stuff before that. Okay, so the first stars. Do I have a slide? I had a slide. Maybe I got rid of it. But anyway, so after the Big Bang, what happened was that the universe was very hot and there was matter and light. Okay, but it was flying around all over the place. But what would happen is that the light would just crash into matter all the time, so it couldn't travel anywhere. Okay, and then at some point, the matter started to come together in a way that we know it. So stuff like hydrogen started to form out of the remnants of the Big Bang. What happened then was there wasn't so much matter that could block the light traveling, and suddenly light was free to move through the universe. Right? We've detected that light. That's called the cosmic microwave background. Okay, so we have a picture of that light. That's the very, very first light that could travel in the universe. Between that and the first stars is called the cosmic dark ages. Okay, where you just had all of this cold hydrogen and some helium lying around. It's possible to see structure. It's possible to see some of that hydrogen using radio telescopes. So things like LOFAR that Peter leads the Irish involvement in, that in principle can see stuff that happened before JWST. So this kind of cold, clumpy material that was distributed out around the small universe as it was then. Yep.
Another question from the front row there. If you were in the middle of the blue
and orange.
Blue and the orange. You're between. Okay, I'll let you answer this. How would you feel?
How would you feel emotionally?
Oh,
physically.
Oh.
You would get a fierce sunburn. Yeah, because the stars up here would emit lots and lots of UV radiation. So if you were sitting on the edge of the cliff here, these are called the cosmic cliffs, by the way. So if you were sitting on the edge of the cliff, you would get a really bad sunburn. Really bad sunburn.
But remember, these little pinpricks of light are kind of the size of our sun. You know, these are enormous things. These are many times the size of our sun. And the edge of that, you probably wouldn't even know that you're on the edge.
Yeah.
But if you're in deep space, that'd be good. All right, adult time. Yes.
Yeah, you said that the scientists are looking at these.
No, that's not, okay, yeah,
So what could we expect in the next few years from
yeah.
research papers?
And so, well, when I said that, I didn't mean they weren't looking at beautiful things. Absolutely. It's that these things were selected. So the way astronomy works is that if scientists want to look at something, they have to write a proposal to get time on the telescope. Okay, so you have to prove that your science is important enough, or at least, win the kind of competition for time to look at whatever you're interested in with the telescope. Okay, that process happened a year before launch. Okay, so all of those targets were protected by that system. Okay, so almost a full year's worth of observations were people who won proposals and won observing time using this system. So the targets that were selected to be released to the public at the start could not be in that pool of objects. Okay, because then you kind of violate the agreement that, that team or whoever wrote the proposal gets to analyze and release that data first, because all of this was released straight away. Okay, so these objects were selected because nobody had asked to look at them. So when I say that, I didn't mean they were looking at boring sciencey stuff. Absolutely looking at amazing stuff. Okay, so then the question was, well, what are we expecting? I shouldn't say, but I think it's going to observe Saturn next week. Okay, so you might see an image of Saturn in the near future. There are things like protostellar outflows, galaxies, all the planetary work, like there's surveys going on of exoplanets, like I showed, to get the composition and spectra of exoplanets, lots and lots of exoplanets, right? Not just one or two, of different sizes and different, super Earths and so on. All of that's being done in the first year. So you will see the results of that. You will see the results of studies like these things, protostars, in very early stages of star formation. Work that's just dedicated to that. Stuff on black holes. It's pretty much everything. I mean, anything you can think of. The biggest things are, the exoplanets is always everybody's favorite. Everybody wants to know, will it detect something really interesting? The images of Saturn should be great. They'd be really nice. I'm trying to think.
Is there a parking attendant for the question?
Yeah. What is your intention now? At the end of the telescope? What would you do at the end of this lifetime? You crashing into a meteorite or drift away in space?
Drift away in space. It's located. It's not in lower orbit or anything. It's quite far away. Actually, it's about six times the distance of the moon. So it's out well beyond the moon, right? It sits at a point in space that is kind of a gravitational null point. All that means is that everything is pulling on the same point with equal amounts. So it's very easy to keep something in that point in space, which means you don't use very much fuel. Okay, so that's why it's there. Also to keep it cold, because it's if you're near the Earth, things are going to be warm. When you're out past the orbit of the moon, you can keep the sun shield pointed at the moon, the Earth, and the sun all in the same direction. Okay. In 20 years' time, I don't know if Elon Musk or some other billionaire will have built a rocket to go out and catch it. It does have a hook. Would you believe? Yeah.
Was that the valuable material you mentioned, gold and some aluminium? Surely you'd want that back.
Yeah. There's a hook on it because it's policy now that anything you put into space has to have some sort of. Yeah, exactly. Yeah. So anything that's put up these days has to have some way that something can grab onto it and bring it back. The idea I don't think it would be brought back to be reused. It would be brought back to put in the museum if this happened. I don't know.
So you said that there was some.
And I should say, and Fiona and our parking attendants are transition year students from Belvedere College. So they're here parking, helping park their cars tonight, but also they have to come to the lectures as well and learn a bit of astronomy. And maybe when you start that company that's going to be a billionaire, go to take a telescope. All right, I think we have time for 2 more questions, 1 adult, and we shall finish with 5. Okay. You're an adult.
Yeah, the one between the scale of, use, stating that one is the artificially used color.
Yep.
Right? And, is it something where, somebody is sitting there and saying, oh, that people will pink, will blue here. Is that how this color comes up, part of pictures, or is that more science?
There's more science. Okay, so the first thing is that because it's heat radiation, you can't see it, right? So you have to attach some color to it, so it can be displayed on a computer screen. Okay, now the colors are the colors that our eyes can see are red, green, and blue. So what you do is you take images from 3 different filters, 3 different parts of the infrared radiation, and combine them as red, green, and blue, and that will give you a color image like this, a false color. It's called false color image. It's normally the case that what's hotter is given blue color. Okay, that's why you see up here where the mass is being evaporated off the top of the cliffs, that's hotter material. Where the red stuff is called colder, and green is in blue. Okay, so for this image is red, green, and blue. For the very last image I showed, for most of these actually it's red, green, and blue, but for this one I think they took some artistic license just to give it that orange hue and this darkness. I mean, you can play around with it all you like, but traditionally it's red, green, and blue, where blue is hotter or more energetic and red is colder or less energetic.
Thank you.
Any questions back then here? And back to 2 very enthusiastic children that are going to have to be. So if not, it's to you. Last question.
The origin did that actually even how?
Do they move?
Yeah.
Yes. So what you're seeing here, I mean, you can see that there's this kind of like finger-like quality. Okay. What's happening here is that there's massive stars out here that their wind is very, very powerful. It's like a real wind moving into some. They're moving across this string. These things here are very, very dense. Okay, so there's a lot of stuff to move. But here where it's less dense, and here can actually move things quite a bit. What you're seeing is that wind coming and leaving the really thick, dense clouds, pushing everything else back. So it is, yeah, absolutely, it is moving. If you could look at this now, I don't know the time scale. It's reasonably far at it. So I don't know how much it would move in a year, for example, but maybe I'd have to do the calculation. I don't know if over the course of 20 years of observing, would you actually see some movement in it.
But the wind is probably going at 1,000.
The wind is going at 1,000 kilometers a second or more. Yeah.
So it's very, very fast.
Yeah.
And if you think about these winds, so our sun has a wind as well, and the wind from the sun blows through the solar system and hits our atmosphere and creates the northern lights. And then it goes the whole way past all of our planets to create a bubble around the solar system. That bubble is where we live in. So the solar wind is blowing things out. But yeah, there's a special instrument called a spectrometer. You can make the spectrometer point at this, and you can work out how fast it's going, and you use the thing called the Doppler effect, which is like when an ambulance is coming towards you, but the pitch changes. We can use that shift in sound or light in this case, work out how fast things are going. But it's a really good question. Loads of great questions tonight. So let's thank Paddy again for coming on. Love this man has every day. It's actually, there is a lot of hard work and pain and crying that probably goes on in the background at times, but no, this testament to all the hard work is amazing. So thank you so much, Paddy, for this. And if you got here late, you can turn up some other time. We're going to have open nights starting very soon. So you can come along, explore the building, explore the campus. We'll have the telescopes open. If it's cloudy, we won't see anything. If it isn't cloudy, we might see something. But do come along, have a look at the website. We just released tickets today. They go pretty quickly, so have a look. And then there'll be loads of open nights after Christmas as well. So thank you very much. Be safe going out that way. Lots of trip hazards, so just be careful. And we'll see you again back in Dundee. Thank you.